Hello and welcome. We're now discussing section 2.7, derivatives and rates of change. And this section brings us back to the concepts at the beginning of this chapter when we started out. We were talking about an object that would be falling close to the Earth and undergoing the influence of the force of gravity on that object as it pulls it towards the Earth. The object would experience a force, the force of gravity, in the rate of change of the object's velocity. It was the object's momentum which was changing, and if the mass was constant, then that force was entirely applied to its velocity. It might be a wise idea to revisit the introduction to that first section, section 2.1, on tangent and velocity problems. To see again that we modeled the change of velocity by using a car on a track. We calculated the average velocity over different space intervals and different time intervals by changing the distance and associating it with the time that it took for the car to travel that distance. We were able to calculate the average speed by interpreting it as a change in position over time. So as we were to vary the distance, the time traveled would also vary, but the ratio of distance to time would change as well, indicating that the speed of the object was changing. That is, that there was an acceleration, and that acceleration was due to the force of gravity as well. Then we wanted to further analyze this change in velocity by focusing on smaller and smaller intervals of time and intervals of space, until we can get to the instantaneous rate of change of the velocity, so that we can get a better picture of how things are changing as they are in motion by looking at it point by point. So we developed the idea of rate of change, which geometrically is interpreted as the slope of a line. We then decided that geometrically we would need to push 2 points on a curve closer and closer together, updating the secant lines that we are using to get smaller and smaller intervals of distance or intervals of time, whichever one, so that we can approach, in the sense of a limit, the instantaneous rate of change, which we could interpret as the instantaneous velocity of the object. So here we are, we returned full circle to that concept. And in order to fully be able to develop this idea, the instantaneous rate of change, we really needed to rigorously investigate the types of limits that we can take, what it means to take a limit, what it means for a limit to exist or not exist, and different types of functions and different types of discontinuities about which we might want to evaluate limits. And here are our objectives for section 2.7, derivatives and rates of change. The slope of a secant line, which we can interpret geometrically as the slope of a line, but formulaically by either of these two formulas here. This is between a fixed point, I've plotted a fixed point here in red, and a moving point, a point that is going to get closer and closer to the fixed point. The slope of the tangent line to f of x at x equals a we interpret as the instantaneous rate of change. That is found by taking the limit as either h goes to 0 or x approaches a. That is describing symbolically that we are pushing the 2 points together. The notation we have for what we've calculated here, that slope of the tangent line, which we interpret as instantaneous rate of change, we call that the derivative of the function f at the value a for the input. And one of the notations we have for the derivative is this f prime of a. So we refer to that symbol as the prime symbol. And this is Newton's notation. This is the notation for when we are taking the derivative of a single variable function with respect to its one and only input variable, and plugging in a chosen value for that variable as well, and the variable value we're choosing to plug in is a. So this is Newton's notation here. Newton's prime notation. And this notation, again, we call it the derivative of the function f at a. The derivative of f at a. F is taken to be a single variable function. Okay, that is, there is only one variable that is an input for this function, and that variable is either x or t most of the time, or it can be theta, for example. So we take the derivative of that function with respect to that input variable. Okay, that is, in the epsilon delta precise definition of the limit, okay, the input variable, usually the variable x, is the one that we have independent control over. That's the one whereby closeness is determined by delta. It is the output of that function, that we have dependent control over. Okay? We are taking the derivative of functions with respect to its input variable. Right? We're controlling the input variable. And we're trying to get the input variable as close as possible to the value a in the sense of a limit, without necessarily letting the value of the variable equal a. We saw with continuity, section 2.5, that the limit of a function where if it is continuous at the point, you could evaluate a limit by plugging in the value instead. Okay? But it does not negate the fact that still, when we are running a limit, and every time we take a derivative, we are formulaically running a limit. We are choosing values of the input variable, let's say x, as it gets closer and closer to a, but not actually at a itself. Our interpretation of it is, this is going to be the slope of the function at that fixed point, in the sense of the limit. The closer we get to that fixed point, the closer that the slopes of the secant lines are to getting to this slope of the tangent line at that fixed point. So this quantity f prime of a is a number. It is always going to equal a number, and that number is the slope of the function at that point. Okay. By contrast, you will see in the future, in a later section, and certainly on a lot of resources, you will see f prime of x, or f prime of t, or f prime of theta. That notation also refers to a derivative, but I'm making a note right now that this represents a function of derivatives. That is, that there is still the variable x floating around in the expression. So if you're looking at an expression like f prime of x is equal to 2 times x equals 2x, that is a function that exists anywhere where it might be defined. That is, for any value x in the domain that you choose to plug in, you can then evaluate what is the derivative at that point. But when you see something like f prime of 1 is equal to 2, which is what we would get by plugging 1 into this, notice this is a number. So this is interpreted as the slope of the tangent line to the function f of x, whichever function that may have been, okay, at the point where x is equal to 1. This is a number, and that's what we're talking about finding right now. F prime of a, so that's a specific number. We are not yet talking about this. This is a function whereby the input is still variable. Okay? And that's something for us to take a look at in a future section. Okay, so a little note on notation there, and the the difference between f prime of a and f prime of x. Okay, x is a variable, a is a fixed value, a constant chosen for that variable. Now that we have the slope of a tangent line, okay, the slope of a tangent line, and since we already have a point on the tangent line geometrically, right, geometrically now, the tangent line would be the line that has the same point on the curve, that fixed point right there, that point with coordinates a, f of a, and it has the same slope as the curve as well. So this green line here, that would be our tangent line. So notice that the tangent line itself, of course, has its slope. M is equal to f prime of a. That is the slope of the tangent line, f prime of a, found by taking the derivative by using a limit. And there's a point on the tangent line, the same point that was on the curve where it's fixed, the point with coordinates a, f of a. All right? So this point right here is the point with coordinates a, f of a. How can we write the equation of the tangent line now? This goes back to algebra. In algebra, if we had an x value and a y value and we knew the slope, then we could write the equation of the line. So recall that in algebra, okay, the equation of the line, okay, that has a slope equal to m, okay, and has a point with coordinates, let's say x1, y1, the equation of that line can be written in the form y minus y1 equals m times x minus x1. Right? That was the point slope form for the equation of a line. If we know the slope and if we have a point on the line, then this is one way that we can write the equation of that line. Okay? You can also transform this into a slope-intercept form, y equals mx plus b. By isolating y, we could add y1 to the other side, distribute the m, combine the like terms, and we can get a y equals mx plus b slope-intercept form of the equation of the line as well. But given the geometry here, we're always going to have a point on the tangent line, a, f of a, the fixed point, and we're going to have the slope of the tangent line as well. The slope is the derivative at the input value a. Okay, so this is our fixed point. Okay. Now translate this equation here, okay, into the equation of a tangent line. Well, if y1 is f of a, and x1 is a, and m is f prime of a, then the equation of the tangent line would be y minus f of a equals f prime of a times the quantity x minus a. So using our notation now from calculus, that is exactly our equation of the tangent line. Here's f prime of a, right, and f prime of a is our slope. That is our instantaneous rate of change. Okay, our f of a, that's our y1, and a is our x1. So there's our point, there's our slope. If we wanted this in slope-intercept form, again, we could add f of a to the other side, distribute f prime of a, combine like terms, essentially isolating y, we would be able to write it in the form y equals mx plus b as well, if we would like to have that form instead. So we are back to algebra at this point. We have when we have a slope and a point, can we write the equation of the associated line? In the world of calculus, finding that slope is the trick here. We have to apply a limit to a difference quotient, right, where the difference quotient represented the slopes of secant lines. We have to apply the limit to that for a variety of types of functions we could run into, so we need to be able to do this limit if we have a polynomial function, or a radical function, or a rational function. And as we move ahead, we're going to want to see how we would run this limit to calculate this slope and this derivative for other types of functions such as trigonometric functions and inverse trigonometric functions, exponential functions, logarithmic functions. Okay. All right, so some more on notation, rates of change and delta notation. Okay, this triangle is the uppercase Greek letter delta. We can interpret it as meaning a difference or a distance, okay? A difference meaning subtraction. So if we write delta y, also we can call that the change in y. Okay, delta y is the difference between two y values, like y2 minus y1, what we otherwise in algebra would have called the rise, right, between 2 points when calculating the rise over run to find the slope of a line. Delta y is notation we have for the rise. Hey, this could be negative. It would be negative if y1 was more than y2, in which case it would be a negative rise, which we can interpret as a fall as well, right? But it is the difference in y values using function notation. That's the same as saying f of x2 minus f of x1. Okay, and delta x is the run, x2 minus x1. So if we write delta y over delta x, that is the same as saying we're taking the rise over the run, right? That's y2 minus y1 over x2 minus x1, or in function notation, f of x2 minus f of x1 over x2 minus x1. Okay, it's another notation that we have for saying that we're doing this. Now, in terms of the instantaneous rate of change then, okay, back to the derivative. This is another way we can write that we are taking the derivative of a function at a fixed point. And generally speaking, we're going to use this for the notation when it is x1, where the fixed point is located. That way it is consistent with our other definitions of the derivative that we've been using, right? We were previously we were using that the second value in the denominator was a. That was the fixed value. And we had the limit was x was approaching a. In other words, if we can remove any removable discontinuity in the limit, we would plug in a as the value of x. So we'd be evaluating the slope by plugging a into the limit. Okay, so x1 right here, right? X1 takes the place of a in this formula. All right, so this can be interpreted as the derivative of the function f at the fixed point with where the input variable's value is x1. And we're using the notation here, delta x approaches 0. Well, delta x is the same as h. Delta x is the difference between the x values. Right? So x2 minus x1, that could have been written as a plus h minus a. Right? But what is a plus h minus a? That's just h. So it's another notation we have for expressing the same idea. And sometimes it's beneficial to have this other notation. In fact, this lends itself well to the other primary notation that is used when looking at a derivative, and that is the Leibniz notation. Leibniz notation for the derivative would be to write something like df over dx, and then we would evaluate that at x is equal to x1. It means the same thing as f prime of x1 would mean. Okay, it's using different notation by a different mathematician, but it does lend itself to more generalized examples, and also allows for us to consider this notation instead if we had multivariable functions. If we were taking the derivative, but there was more than one input variable to choose from, the Leibniz notation specifies in the denominator which variable it is we're taking the derivative with respect to, in fact. Okay, something that the Newton notation doesn't happen to do. Okay, so for different situations, we're going to use different notation, and just sort of has the flexibility to get used to the different types of notation. Okay, later as we apply it to more and more applications, we'll need to be more versatile. Okay, in choosing the notation and reading the notation. Okay, but they all, geometrically, these all mean the same thing. And here they are, right? So f prime of a, okay, I'll tag one more on here. That one more would be the Leibniz notation. Okay, another way to interpret this, right? So f prime of a is this limit as h goes to 0 of this ratio. Notice there is no x in this ratio. Right? A has already been plugged in. Over here, there is an x. Why is that? When we run the limit, x is approaching a. That is, we're going to be replacing x with values that are getting closer and closer and closer to a. And if we can remove the discontinuity here, then we can just plug in a, as long as we have a continuous function. Are we going to have a discontinuity here? What happens if you plugged a in for x right now? If you plugged a in for x right now, notice we're going to get f of a minus f of a over a minus a, which of course equals 0 over 0. No matter what function we're choosing, this would be true. When we run this limit, that's exactly what we're going to get, regardless of the function we actually started with. Okay, and we're not taking the limit of the function, by the way. We're not taking the limit of f of x. We're taking the limit of the difference quotient now when we're evaluating the derivative. Same result we would have had over here. If you plugged 0 in for h over here, you're going to get f of a minus f of a over 0. So you're going to have 0 over 0. Right? So you're going to have to remove the discontinuity. And if we do that and we have a continuous function as the result, then we're allowed to plug the value in. So we're going to be plugging a into this after removing the discontinuity. So ultimately this will just be a number. Right? This expression will just turn into a number. all right, and will no longer have an x in it. Same thing's going to happen here. Again, we have delta x is approaching 0, so we're approaching the fixed value, x1 in this case, so ultimately this is going to output a numerical value. Because x1 is taken to be a particular value of x that is going to be plugged in. And again, full circle back to where we started at the beginning of this chapter. We're dealing with, in many cases, we're dealing with the applications of finding velocities and rates of change. Velocity is the rate of change of position with respect to time. And the time rate of change of velocity is acceleration. So here we are defining how to find the velocity function as a derivative. We will later extend this idea to finding acceleration functions by taking the rate of change that is the derivative of velocity in order to get acceleration. In other words, we'll be taking derivatives of derivatives in the near future as well. Okay? So if you have a position function, so that is to say, if there is an object that starts at some point, we'll just label its starting point as 0. That can be, that can be where you started an experiment. It was at position 0, or it can be as you were observing an object. It could be where you started recording your observations. So imagine an object floating through the sky, flying through the sky or orbiting the planet or something like that. You can say its position at 0 is whenever you started recording its position. It doesn't mean that it started there, but instead that it started, you started your experiment or your observation at that point. In the case of the demonstration at the beginning of this semester, with the car on the Connects tracks, 0 can be thought of as wherever the starting point of the car was when it was released from there. And the car would move forward down the track. Okay. It would move down the track, and it would accelerate as it is moving in this direction. Okay, and it would just keep going. Well, suppose that we were to take some particular interval of either time or distance and measure the difference in the distances. That is, what we are measuring here are the positions of the object. So let's say this were units, the position units, let's say it were in inches, like the car was traveling down the track and I measured it initially have 33 inches of track. So it starts at the top at 0 inches, and after it has traveled some particular distance, that distance would be f of a, or s of a. So s is often used to represent the output of a position function. Okay. H, by the way, h can also sometimes be used for a height function, h of t. Can you think of a reason why, if we're doing calculus and we're running these limits, why might we not want to choose the function to be called h of t? Why could that create confusion? Well, we are already using h to mean something else in the interpretation of the derivative. If we did have a function called h of t as a height function, let's say we were dropping an object, another thing that we talked about previously in that section 2.1. If you're dropping an object and, if we did refer to its position as the height of the object above the ground, for example, we might prefer to not use the definition of the derivative where h is going to 0 because we're already using h for expressing height. We may want to choose a different variable for h, or we may want to choose a different form, all right, in the notation for our derivative because of the fact that h is now being used to represent something else. Okay? Or we may want to call this capital H of t, maybe. Okay, maybe I can use that for the height function. Right? Some things to consider. So f of a is just in general telling us the position of the object relative to whatever our observation starting point was. Relative to there, it's telling us what the position is. Okay, if this object we choose ahead of time which direction is positive, which is negative. So if this object is moving to the right according to the observer, we might choose to say that this is a positive displacement. Then, okay, a change in distance that was positive. To an observer who would have seen the object instead moving to the left of the initial point, they may assign a negative quantity to that distance. Okay, so we have the magnitude The magnitude of that quantity tells us how far it traveled, but the sign, plus or minus, of that quantity can tell us the direction it was traveling relative to the observation point. Okay? It's all relative to the observer. If you could go through the screen and go to the other side and look back at this image right here, this would actually not be traveling to the right. To an observer on the other side of the screen, or on the inside, through the mirror looking back, if you will, this same object traveling this direction would actually be traveling to the left according to that observer. Right? So it's really relative to whoever's making the observation. So this is the actual position of the object, whatever that is, and this is another position of the object. And the difference between these two positions would be the change in position, that is a delta S or a delta Y or a delta F, right? The delta S, the change in the position, okay, which we can then associate to the change in the input variable, the change in time, okay? A change in position with respect to a change in time, all right, position over time, that gives us a velocity. Again, velocity tells us more than just how fast the object is moving, but the direction it's moving. If this thing is moving to the right, so that is that the position is increasing and remaining positive, then we're going to interpret the velocity as positive as well. If the object were to stop, turn around, and go back the other direction, if it were going the other direction instead, then this difference right here would actually be a negative difference, and we would get a negative velocity. And even if the speed is the same in both directions, the sign, plus or minus, of that velocity indicates to us what direction it's actually traveling. So the velocity can be taken from the position function itself by calculating the derivative, the instantaneous velocity, that is. The average velocity is the same as the slope of a secant line, right? The difference quotient. The instantaneous velocity is the limit of that difference quotient. Okay? And a note, speed is the absolute value of velocity. So if you wanted to know the speed of the object, okay, if you calculate this derivative of the position function, if you get a negative quantity, that would be the velocity. You take the absolute value of that, flipping it to positive, and that would be interpreted as the speed of the object instead. Okay, so here we were back in section 2.1 where we were defining a fixed point. That point is not moving anywhere. It's going to be stuck right there. We want to keep it still. And then we would choose another point either to the right or to the left, right? We did this in both directions, right? We would choose a point to the right, move it towards the fixed point, and we would choose a point to the left, move it towards the fixed point. So we would be looking at intervals to the right and intervals to the left of the fixed point. So now let's name the coordinates for this fixed point. One name we could have for it is a plus h. That is, we have added some, in this case, some positive quantity to a. That's why we're to the right. If we had a point over here, we could also call that a plus h for the input, where h would have been negative instead. That's one option we have. Adding a negative number, that would give us, that would give us a quantity to the left. All right, so without loss of generality, okay, meaning even though we can do this all to the left, the same thing, let's just focus on looking at it to the right for now, and just know that the process is very similar if we were to look at this from the left as well. So here's the input variable's value is a plus h. What is the output going to equal? It's going to be f of a plus h. So this point then has the coordinates a plus h, comma, f of a plus h. Okay? So the idea here that we have geometrically is now we want to know what is the slope of this line, and that is a secant line, and the slope of that line can be found by taking y2 minus y1 over x2 minus x1 for the 2 points that we already know exist on that line, and that's going to give us this formula right here, f of a plus h minus f of a over a plus h minus a, which just simplifies to h, right? Now suppose that instead of calling this a plus h, right, we have another option here. Let's say we called this instead x. In other words, we're allowing something else to vary right now. Well, then this point right here would be the point with coordinates x, f of x, right, input, output. Okay. Now we're still calling this a f of a. Okay, and then we would say, well, the slope of this line then, okay, so in purple, so the slope of this line is between the point a f of a and x f of x. And that slope would be this formula right here. And now, instead of pushing a plus h towards a, like we were doing earlier, right? Earlier we're doing this. We're pushing this point towards that point by allowing h to shrink towards 0. Now what we're doing is we're pushing x towards a when we try to calculate the slope of the tangent line, right? The instantaneous rate of change. Okay. Now we have one more type of notation. Okay. Oh, didn't use dark blue. Here we go. Okay, dark blue. Now let's say if we call this x1 and we call this x2, okay, well then this point would be what? This would be the point x2, f of x2, and this point right here, we could call instead, I'll put that up here, x1, f of x1. Okay, so then we'd be using the formula for slope, that is f of x2 minus f of x1 over x2 minus x1, which, using the delta notation, we can also simplify as delta y over delta x, for example. It's another way to write exactly the same quantity. All right? We're calculating, in all three of these formulas, we're calculating the slope of that secant line. And then we are applying the limit in all cases, right? In the delta x, delta y, delta x notation, we're taking delta x to approach 0. As delta x approaches 0, it's the same as saying x2 is approaching x1. All right? Okay, and we are calculating from that geometrically the slope of the tangent line. We interpret it as the instantaneous rate of change. Okay? And we'll call that thing f prime of a, or f prime of x1, if this was the case that we're using this notation. Okay, well, let's deal with some examples using f prime of a notation now. Okay, so I have included for you a worksheet here. Some of the exercises I could ask you to do. First, use the definition of the derivative. That is, in other words, using the limit definition. Running a limit, find out what the derivative is. Be careful with the instructions here. When I ask you to use the definition of the derivative, I mean you need to run the limit, and you need to find it by use of a limit, and that also is how you need to show your work. We will get into later, for those of you who have seen calculus before, later on in the course, we'll get into formulas for finding the derivatives when they exist. This right now is an investigation for where the derivative comes from and how the limit can be used to find the derivative, and that's what we're doing. Okay? So using this definition of the derivative, find f prime of a at the given value of a. Okay, I give you a polynomial function here. Here's a rational function, 1 over x squared. Okay. Here is a fractional function where we have a radical in the denominator. Okay, and here's another polynomial one here as well. Okay, so let's pick one of these. Okay, this one looks like fun right here. Let's do this one right here. Okay, and then what are we going to do later, by the way? After we find the derivative, the next objectives, right? How about finding the equations of tangent lines? Okay, so of course, as we saw in the development of the formula, the derivative plays a huge role in that. The derivative at a point tells us the slope of the tangent line. And then, of course, the point itself is an x and a y value on the line. Okay, the x value here, the x value in this case, x equals 8, that's our fixed value. That's a. So that's telling us how to evaluate the derivative. Okay, or it tells us where to evaluate the derivative to find a particular slope. So we have all the information we need here. We have a function, we have a fixed point. All the information we need here so that we can then calculate the slope of the tangent line by use of the limit definition of the derivative and use that slope along with the given point to write ourselves an equation of that line. The next thing is to sort of do some little reverse engineering here. If we were looking at one of these limit expressions, can we determine what the function is and what the value a is that we are that we're looking at, whereby these would be calculated as a derivative of that function at a particular point. Okay, let's try this example right here. That f of x is 4 over root 1 minus x, and a equals negative 3. That is, we're going to use the definition of the derivative to find f prime of a. Okay, so find f prime of a. Again, to be clear, this is what we're working on now. We're using limits in order to do this. Find f prime of a using the limit, okay, where the function f of x was given to us as 4 over root 1 minus x, and the value of a is negative 3. Okay, so f prime of a, let's write down the formula in general. Okay, the f prime of a is the limit as x approaches a of f of x minus f of a over x minus a. That's not the only formula we had, but that's one of them. Okay, so for this example, a is negative 3, so we're talking about f prime of negative 3, and that's equal to the limit as x approaches negative 3, f of x, which is 4 over root 1 minus x, minus f of a, that is f of negative 3. So that's going to be 4 over the square root of 1 minus negative 3, okay, over x minus a, that would be x minus negative 3. All right, so plugged into the formula. And so now we have some algebra to do here to help simplify our difference quotient, and then we have some calculus to do when we run the limit. And we need to keep writing limit until we actually are able to evaluate it, right? That's part of the notation here. Okay, so notation. Make sure you watch your notation there. You're writing limit until the point where you've actually evaluated the limit. Now what happens, maybe this thing is already continuous. Maybe we can just plug in negative 3, right? What's going to happen if we plug negative 3 into the function on the top and the bottom? Right? What are we going to get? Okay. All right, as we've investigated before, no matter what, if we plug a in for x when we are into one of these difference quotients, we're always going to get the same thing. We're going to get 0 over 0, which is an indeterminate form and which indicates there is a removable discontinuity. Depending on the type of function we have, the family that we happen to be looking at, that's going to determine how to remove the discontinuity. For example, if we had polynomials here, okay, which we don't right now, if we had polynomials, we would factor the polynomials to remove the discontinuity. What do we do, though, when we have ratios, that is fractions? And what do we do when we have radicals? Okay, those are the techniques that we need to apply here. We can't just plug in the negative 3. It'll give us indeterminate. Okay, let's do a little simplifying here, though. I'd like to do that. X goes to negative 3. 4 over root 1 minus x minus 4 over, this is the square root of 4, right? So square root of 4 is just 2. Okay, I'll just go ahead and I'll simplify that right now down to 2. Okay, and the denominator is x plus 3. Plugging in negative 3, we get 2 minus 2 over negative 3 plus 3. That's 0 over 0. Okay, so what do we do now? Okay, well, we have a denominator here to deal with. That's one thing. We could combine these terms in the numerator with a least common denominator. Okay, that's something we can try. The limit as x goes to negative 3. So this will be what? 4 minus 2 root 1 minus x over root 1 minus x. And then that's all over x plus 3, right? Okay, now, dividing this by x plus 3 is the same as, right, multiplying by the reciprocal of this. So this would be the same as writing this as times x plus 3. Right? As a reminder, a over b divided by c over d, that's the same as a over b divided by c over d, like that. All right? Which is the same as a over b times d over c. In other words, these two denominators are going to combine, and these two numerators would combine as well. All right. So remembering our algebra, Okay, so right now I'll note that we can factor out the constant 2 from the numerator from both terms, and by the limit laws, we can then factor that 2 out of the entire limit. So this is the same as 2 times the limit x goes to -3 of 2 minus root 1 minus x over root 1 minus x times x plus 3. Right? So take a look at limit laws. Okay? So I've taken a constant out of the function. So when you take the limit of a constant times a function, you can put the constant in front of the limit. Okay. And so now we need to remove this discontinuity from the numerator, right? So we're going to multiply the top and the bottom by the conjugate of the numerator. Okay, so we get 2 times the limit x approaches -3. Now the numerator will become what? 4 minus the quantity 1 minus x. Alright. The denominator, we have root 1 minus x. We have x plus 3. We have 2 plus root 1 minus x. Okay, let's see if we can remove that discontinuity. 4 minus 1 minus x is the same as 3 plus x. Right? 3 plus x. So in the denominator, we also have x plus 3. Okay, and then let's say I distribute this root 1 minus x now. We get 2 root 1 minus x plus 1 minus x down there. Okay, and now we can cancel x plus 3 with 3 plus x. So we get 2 times the limit x approaches -3 of 1 over 2 root 1 minus x plus 1 minus x. Okay, so now the numerator is constant. Let's rerun the limit at this point and see what we get. So we plug in a -3. This is going to be 4, the square root of 4. That's fine. And then we're going to get 1 minus -3. So we get 2 times 1 over 2 square root 4 plus 1 plus 3. Okay, so that is what? 2 over 4 plus 4. Okay, that's 2/8, or that is equal to 1/4. So what did we find? We found f prime of a using the limit definition, right? For this function, 4 over root 1 minus x, where a is equal to -3. Okay, so we found that f prime of -3 is equal to 1/4. And that's for the function f of x equals 4 over root 1 minus x, okay, where a was equal to -3. Okay, let's go a little further than this then. Let's now find the equation, or I don't want to say the, I'll say n equation, because there's more than one way to write the n equation of a line. Find n equation of the tangent line to the function f of x equals 4 over root 1 minus x, okay, if x is equal to -3. In other words, at the point -3, comma, f of -3, right? Well, what point is that? Okay, where f of -3, okay, is equal to 4 over the square root of 1 minus -3 minus, so 1 plus 3, which is 4, right? And 4 over root 4 is just equal to 2, right? So we are at the point -3, 2. Okay. We're at the point -3, 2 because the input was -3 on the function f of x equals 4 over root 1 minus x, and we are seeking the equation of the tangent line. Well, the equation of the tangent line y minus y1 equals m times x minus x1, the point slope form of the equation of the tangent line. And the equation of that tangent line in function notation would be, for this case, y minus f of negative 3 equals f prime of negative 3, that is the slope of the tangent line where the input is negative 3, okay, times x minus negative 3. Okay, so let's plug in what we know. All right, we know that f prime of negative 3, right now, f prime of negative 3 is equal to 1/4. So that is the slope of the tangent line then. Okay, so 1/4. Okay. F of negative 3, we evaluated up here, that was equal to 2. So y minus 2 equals 1/4, and then x minus negative 3, that gives us x plus 3. This is, therefore, an equation of the tangent line. Okay, it has a slope equal to 1/4, and it goes through the point negative 3, 2, and that point is on the line and on the curve, right? So that's a point where the curve intersects the line. Okay, so a geometric feature of the tangent line to a curve at a point is that the tangent line and the curve share the point in common, and they share the same direction, the same slope at that point. An instantaneous rate of change, an instantaneous slope. Now, what if we wanted the slope-intercept form for the equation of this line? Okay, right, we just used point-slope right here. Point-slope form of the equation of the line. What if we wanted slope-intercept? Okay, which can be helpful if we want to express this as a function, that is to solve it for y. What if we wanted y equals mx plus b form? Well, we can get that by adding 2 to the other side, distributing the 1/4, and combining like terms. So we have y is equal to, let's see, 1/4 x plus 3/4, and then plus 2. And then we can combine these like terms right here. So y equals 1/4 x plus, that's 8/4 and 3/4, which is 11/4. And that would be the slope-intercept form of the equation of the line. Now, notice geometrically here, the related to the symbolic form of the equation, the information that is contained within this equation right here is advantageous to us for this example, because we can read right from the equation what is the direction or the slope, the instantaneous rate of change, that is this number right here, and what is the point that the tangent line shares with the curve. Negative 3, 2 is that point. So we know exactly where they merge with each other. That's helpful analytically, okay, geometrically as well. When we look at the slope-intercept form of the equation of the line, we get that the slope is the same as the instantaneous rate of change, but we don't have information about the actual point where they merge. Instead, we have information about the y-intercept, which for certain applications is very valuable information. Again, it depends on what it is we're trying to do next. If the instructions to the exercise, as they were here, the instructions are find an equation of the tangent line, if it doesn't specify what type of equation, you can really just go for whatever is the quickest, easiest equation of the line that you can find, which in this case was this, because we had point and slope information. Okay? If you're directed to find the slope-intercept form of the equation, then you can do that. And if we had some other steps to take in the process after doing this, if we were asked something else, then we might want to use whatever we're asked to determine which form is the form we should actually, we want to proceed with. Okay, so I'm just saying find an equation of the tangent line. I gave you 2 different forms of that equation right here. Okay, but with the given information of a point and a slope, this was the quickest, the point-slope form for that equation. Okay, so back to the worksheet. So I went a little further than just finding the derivative on this example, right? And of course we got to do apply the techniques of using a common denominator. We also used a limit law, more than one limit law in there, but I used a limit law where I factored out a constant, and we used the conjugate in order to deal with a removable discontinuity in the form of a radical. The polynomial example in A and D expect to run the limit on polynomials. When you have an indeterminate form 0 over 0 with polynomials, recall the strategy that we use to run those limits has to do with the factor theorem. And this example here is a rational function. Again, combining ratios, you use a common denominator. Okay, so you can run the limit. Okay, run the limit on the difference quotient for this function right here. Okay, remove the discontinuity as needed. Now here's a radical function. The information is just given in a slightly different form. Instead of telling you a equals 8, instead we're given the point. That is, you should be able to verify that this point is certainly on this curve, and it is. If you plug 8 in as the value x, you get y is equal to 3. The square root of 9 is 3. So this is certainly a point on the curve. Furthermore, this is supposed to be a point on the tangent line as well. So you're finding the equation of the tangent line to this curve where the input is 8, and you can follow the process that I just used there. You need the derivative evaluated at 8 in order to find the slope of the tangent line, and then use that slope along with the x and y values here at the point in order to find the equation of the line. And do the same thing for this, right? What changes between these two examples here is the family that the function belongs to. How do you evaluate a limit with a removable discontinuity if the family is radical? And you think conjugate, okay, in general. How do you remove a removable discontinuity if the function is rational? And start with a common denominator, okay? And then you might get a complex fraction after doing that. We had a complex fraction here, okay? We had a complex fraction here. Go back to this stage right here where we had limit as x goes to -3. Okay, we had this 4 minus 2 root 1 minus x over root 1 minus x over x plus 3. We could say that's x plus 3 over 1. It's a fraction over a fraction, or fractions inside of fractions, which is in general what you're going to get when you're dealing with these ratios of rational or fractional functions. And you deal with it the same way I dealt with it here. You flip the bottom fraction over to multiply it by the top. Essentially, so you're going to be combining these denominators is what's going to happen, and you're going to be combining these numerators together, right? 1 times this numerator right here. Okay. So all the techniques you would need for these examples on the worksheet are built into that one exercise I did right there. Now let's take a look at these type of exercises down here as well. Okay. What is the function? What is the number a? Okay, establish which one of the definitions of the derivative we happen to be looking at in each case. Notice, right, for this exercise right here, we have a limit as x is approaching some constant value. X is approaching a constant value, okay, versus over here where we have the limit as h is approaching 0. That indicates that we're looking at different forms for the definition of the derivative. This is the limit as x approaches a, but this is the limit as h approaches 0. Okay, so that's one thing to take into consideration. The other form that we're not seeing much of in this section, the limit as delta x approaches 0, okay, it's similar to this one right here, the limit as h goes to 0. Okay, but these are the two main forms for this section. So let's take a look at, let's try one of those type of problems out, okay? Let's do that. All right, so that is for each limit represents a derivative. Okay. Determine the function f and the fixed value a. Just paraphrasing here, kind of, such that the given expression, okay, is the derivative of f at a. Okay, and the given expression I'll give you would be the limit as theta approaches pi over 6. Okay, the sine of theta minus 1/2 over theta minus pi over 6. Okay. So I've changed the variable here, the input variable. The input variable now is theta. Okay, what is the function f going to be? Let's take a look at what form this seems to take. Here's a couple of our main forms. The limit as x goes to a of f of x minus f of a over x minus a, or the limit as h goes to 0 of f of a plus h minus f of a over h. Which of these two forms does this seem to resemble more so? Okay. Well, we have a variable approaching a finite value that's not 0, so it looks like it's this first one right here, the limit as x goes to a of f of x minus f of a over x minus a. Okay, so we've replaced x with the variable theta. That is, we're not talking about f of x now, we're talking about f of theta in this case. So we have f of theta. Well, f of theta, in this form, f of theta would simply be the first term of the numerator in this form. Notice that the first term in the numerator is not f of x in the other form, but it is in this form. So f of theta in this case is the sine of theta. Now what's the value of a? Well, the value of a is going to be the constant that we see here in the denominator, right? X minus a. So in this case, that would be pi over 6. Okay, so a is equal to pi over 6. Now, maybe as just a confirmation here to check to see if this is reasonable, what would be f of a? Okay, what is f of a? And that should be this quantity right here, 1/2. Well, f of a would be the sine of pi over 6. And that's pi over 6 radians, right? We can verify that the sine of pi over 6 is in fact equal to 1/2. Okay? So this is in that form. It's f of theta minus f of pi over 6 over theta minus pi over 6. Okay? So I'll write it explicitly for you in that form. The limit as theta goes to pi over 6 of f of theta minus f of pi over 6 over theta minus pi over 6. Okay, now let's try another one. I'd like to give you one in the other form. Same instructions. Okay, find the function f and find the value a. Okay. Okay, such that the expression, the limit expression is f prime of a. And I have the limit as h approaches 0 of, let's see, 4th root of 16 plus h minus 2, okay, over h. Now, notice that if you plug 0 in for h, what do you get? Plug 0 in for h in the numerator. You'll get the 4th root of 16, which is 2, minus 2 over 0, right? So this is going to evaluate as 0 over 0. Okay, so it seems a legitimate difference quotient here. Okay, and it is in the form of the limit as h goes to 0, so f of a plus h minus f of a over h. And we know what h is, but we want to find out what is the function f and what is the value a. Now, how can we find out the value a is a little trickier here, right? Where do we find it? Well, the input in the first term, is a plus h. So a, right? So a can be located here, part of the input. So what's the value of a? In this case, it looks like a is this value here, 16. And now what about f? Okay, is this an f of x, an f of theta, an f of t? Well, it doesn't matter in this case. We can choose any input variable we want, so I'll just call it f of x. Okay, so f of x would be what function? Well, what is it that we're doing to the input a plus h in this case? We're taking, which in this case would be 16 plus h. We're taking the 4th root of it. So f of x would be the 4th root of x. Now, just to verify that this is reasonable, let's take a look at what f of a is, right? What would f of a equal? Well, f of a we would expect to be the 4th root of 16, and the 4th root of 16 is equal to 2, and that's exactly the number we see here. So that's correct. So what we're looking at here, if we are to evaluate this limit, which we're not being asked to evaluate this limit in this exercise, or in the previous one, we're not asked to evaluate it. But geometrically, what is it we would be finding if we had evaluated it? Well, if we took a look at the function, the fourth root of x, okay, if we took a look at a fourth root of x function, y equals the fourth root of x, and if we went out to the point where the input was 16 and the output was 2, okay, that is this point right here with coordinates, not the scale here. This is the point with coordinates 16, 2, right, which certainly exists on this function right here. Okay, then what we're looking at here is what is the slope. Okay, we're looking at what is going to be the slope of the tangent line to the function at that point right there. Okay, so if we had a tangent line right there, okay, the slope of this tangent line, f prime of 16, is what we're looking at here. Okay. All right, and yeah, for good measure. Okay, so this limit here is equal to f prime of 16, okay, where f is the function of fourth root of x. Okay. Up here, what were we looking at then geometrically? We had the function f of theta is equal to the sine of theta. So that's our function whose graph we're interested in here geometrically. Okay, it should go a little bit more like that. Okay, of course it extends in both directions. This continues on and on. Okay, so this is the theta axis and this is the y-axis. Y is equal to f of theta equals sine theta. Okay, at pi over 6, the output was 1/2. All right, so if this is 1 right here, right, 1/2 is about here. Okay, so like this point right here, for example. Okay, and so that's the point with right where the input is pi over 6, the output is 1/2. We're on the sine function, and we're talking about the slope of this. Right, the slope of this tangent line right here. Okay, that's what the limit would evaluate to. Okay, so m is equal to f prime of pi over 6 for this example. Okay, if we can evaluate this limit, okay, which we haven't done this with the trigonometric functions to this point yet. We'll take a look at it in the next chapter. Okay. If we could evaluate this limit, which, note, if we plugged in pi over 6, we're going to get 0 over 0. It's indeterminate. When we can evaluate this limit, we can see that it's not going to be undefined. We can see geometrically here, we expect this to be a positive number. Okay, if we evaluate this limit, we expect to get a positive quantity interpreted geometrically as the slope of this line, which is clearly a positive slope because it rises from the left to the right. Okay, so this limit is going to evaluate as the slope of the tangent line to the curve y equals the sine of theta, okay, from the point pi over 6 1/2, which is a point that is shared by the curve and by the tangent line as well. Okay. All right, now let's take a look at a velocity example. So an application of what we're doing here. The application of velocity and speed. Okay, so a particle moves along a straight line. I mean, like a car that moves along a connects track kind of a thing, right? Particle moves along a straight line with an equation of motion. S is equal to f of t is equal to 10 plus 45 over t plus 1. Okay. Where S, the position, okay, is measured in meters, and t, the time, is measured in seconds. Let's find the velocity. and the speed, and recalling that the speed is the absolute value of velocity. So if the velocity is positive, then the two are the same. If the velocity is 0, the two are the same thing. If the velocity is negative, then the speed would be the absolute value of that velocity would be positive. So find the velocity and the speed of the object when t is equal to 4 seconds. Okay? Find the velocity and the speed when we are given a position function. Right? So this is position. Okay. So when t is equal to 0, if we were to plug 0 into this, we would get 55. And so 55 would be, we could say, the initial position of the object. It could be 55 meters relative to the observer, or 55 meters relative to some other observational point of reference, for example. So, 55 is the initial position relative to something. Okay, and then we can find out what the position is by at 4 seconds by plugging 4 into here. If we plug 4 in, we're going to get 45 over 5 is 9 plus 10 is 19. So it's going to be 19 meters would be its position at 4 seconds. Now let's call the velocity function v of t. Okay, so v of 4, that would be interpreted as the velocity at 4 seconds, recalling that velocity is the time rate of change of position. So v of 4 is the same as s prime of 4. That is, the rate of change of position with respect to time would give us velocity. Okay, which we can also call f prime of 4 because s is the output variable for the function f of t. So we want to find f prime of 4 because the interpretation of that would be the velocity at 4 seconds. Okay, so we have velocity at 4 seconds. It's the rate of change of the position. Now in Leibniz notation, this is the same as saying like ds over dt, where t is equal to 4. Okay, or df over dt, where t is equal to 4. Okay, so it's Newton versus Leibniz notation. Okay, so f prime of 4, well, that is the limit, as the input variable now is t in this example. So as t approaches 4 of, let's see, f of t minus f of 4 over t minus 4. So that's what we want to evaluate. We would interpret that as the instantaneous velocity at 4 seconds. Now what is f of t? 10 plus 45 over t plus 1. Okay, so we have the limit as t approaches 4 of 10 plus 45 over t plus 1. All right, that's our f of t, minus f of 4. What's f of 4? So f of 4 is going to be 10 plus 45 over 5, which is 19. 10 plus 9, so it's 19. So f of 4 is 19, and then the denominator is t minus 4. What's going to happen when we plug t equals 4 into this? Right? This is going to be 19 minus 19 over 4 minus 4, right? So this is going to be 0 over 0, an indeterminate form indicating a removable discontinuity. But we're dealing with a rational function in this case, and we need to remove the discontinuity from our rational function. So let's use our algebraic technique to do so. So I'm going to combine the like terms now because I have a 10 and a minus 19. So that gives a negative 9. So 45 over t plus 1 minus 9 over t minus 4. Okay. So now we have fractions inside of fractions, complex fractions, right? So I'm going to deal with this in this way. I'm going to multiply the top by t plus 1 to distribute it, and multiply the bottom by t plus 1 as well. We'll get exactly the same result as the technique that we had used previously. That is, if we combine these two terms with the denominator t plus 1 and then flip to the denominator and multiplied by the top. All right, it's algebraic simplification of complex rational expressions. If you need to review this type of content, it's complex rational expressions or complex fractional expressions. Complex rational or fractional expressions. Okay, so distributing the t plus 1, we're going to get 45 minus 9 times t plus 1 over, now we get t minus 4 times t plus 1. Should we expand that right now? Well, what are we trying to do? What's our goal? Remember, we got 0 over 0 up here, and that means we want to remove a discontinuity. We are now no longer dealing with rationals. Now we're dealing, we're dealing with a rational, but it's no longer complex. What we're dealing with here is a polynomial over polynomial. And it's still going to be 0 over 0. And recall that in order to remove the discontinuity from a rational expression, we actually want it to remain factored. So I'm not going to distribute in the denominator. Look what happens from the numerator now. So let's see, 45 minus 9t minus 9. In other words, I could factor out a 9 from here and combine some like terms. T minus 4 and t plus 1. Okay, so what is 45 minus 9 is 36, right? So the limit as t approaches 4 of 36 minus 9t over t minus 4 times t plus 1. Now we can factor out from the numerator the constant 9, which can, by limit laws, move to the front of the limit. 9 times the limit t approaches 4 of 4 minus t is left in the numerator. And on the denominator, we have t minus 4 times t plus 1. So now can we cancel out or remove the discontinuity? Well, we have a 4 minus t and a t minus 4, and those are opposites of each other. So if we cancel those out with each other, we'd be left with a negative 1, right? T minus 4 over 4 minus t is equal to negative 1, right? So this equals negative 9. I'm going to pull the negative 1 to the front, again, using a limit law, times the limit as t approaches 4 of 1 over t plus 1. Now we can run the limit. So now finally we don't have to write limit anymore. We have negative 9 times 1 over 5, which is negative 9 over 5, or as a decimal, because this will give us an exact value as a decimal as well, negative 1.8. What did we just find? We just found f prime of 4, which is the velocity of the object after 4 seconds. It is velocity. What are the units? The position was in meters. The time was in seconds. So position over time, negative 1.8 meters per second. So this thing is moving at 1.8 meters per second to the left. Okay, it is moving to the left, or right back towards the initial observation point currently. Okay, because we know that its position at 4 seconds was 19, a positive number. So that would seem to indicate that if this is where it started, it is after 4 seconds, it is right here. Remember at the, not where it started. If this is the observation point, all right, then this is relative to its position. If this is a positive number, I take that to mean on a line that it is to the right of the observation point, wherever we're making the measurement from to see what distance it's at. Recall that, the initial position, if we plug 0 in, would put us at 55. So the object started at 55 meters, and that was when time was equal to 0. So that's when we started our observation or experiment or whatever. It started at this point here. After 4 seconds, it was here, right? Right, so it's moving to the left, and because it's moving to the left, right, then we can interpret that the velocity over that interval and the velocity at this instant would be negative because it is moving to the left. Okay, and finally, what is the speed? The speed is the absolute value of the velocity, so the absolute value of v of 4, or the absolute value of f prime of 4, or s prime of 4, the absolute value of it. And that gives us positive 1.8 meters per second, or positive 9/5 meters per second. So there's an application. An application for the derivative as a rate of change, in this case the rate of change of a position function. Okay, so this brings that concept of motion of an object, velocity, it brings it back full circle to where we started at the beginning of the chapter. Okay, we have a context for this. An object is moving, its velocity is changing, that is, it is accelerating or decelerating, and we want to try to figure out what its instantaneous velocity is. Okay, and more applications for this derivative abound for us to look into as we move ahead, as we have a lot of work to do also in determining how to more quickly evaluate these limits and find these derivatives for all types of functions and all types of situations. Okay, that's it for section 2.7. Okay, if you have any questions for me, you can let me know. Good luck with the homework and take care.